All right, let's get right into it. When you think concrete, you probably picture, a sidewalk, a building, just a boring old gray slab, right? But what if I told you it's actually this high-tech chemical marvel? That tiny, simple changes in its recipe can be the difference between a structure that lasts for centuries and one that just crumbles. Today, we're going to unlock the secrets hidden inside this stuff we see every single day.
So yeah, what is that difference? I mean, what separates something like the Pantheon in Rome, still standing after 2,000 years, from a modern bridge that needs serious repairs after just a few decades? It's a question engineers have been absolutely obsessed with for a long, long time.
And the answer, when you get right down to it, is surprisingly simple. It's not about some magical ingredient. It's all about the recipe. Yeah, just like baking. Getting the proportions exactly right is everything. A little too much of this or too little of that, and you end up with something completely different.
And the one key ingredient we're going to zero in on today is water. It seems so basic, right? But the amount of water you use, well, that's the master variable. It pretty much controls everything that happens next. In the world of concrete, this all boils down to something called the water-to-cement ratio. And it's exactly what it sounds like. You just take the weight of the water and divide it by the weight of the cement. It's a simple little number, but as we're about to see, this one ratio is the key to unlocking concrete's real power.
To really get our heads around this, let's tell a little story, a tale of two mixes. We're going to watch two batches of concrete go from a liquid slurry all the way to a solid rock, and there's only one single difference between them: how much water we use.
Okay, meet our competitors. In the left corner, we've got the wet mix. It's got a water-cement ratio of 0.5. So think of it this way. For every 10 pounds of cement, we're adding 5 pounds of water. And in the right corner, we have the dry mix with a ratio of just 0.3. Same exact stuff, just less water. Now, let's see what happens.
This is where the real magic happens. The second you add water to cement, you kick off this incredible chemical reaction. And this is important. The concrete isn't just drying out like a mud puddle. No, it's going through a fundamental transformation at a molecular level. This reaction is called hydration. So at first, the cement particles are just kind of floating around in the water. Then, boom, they start to react, using up both the water and the cement to create something totally new. This new stuff grows and spreads out, acting like a super strong glue that locks all the sand and gravel together into one solid piece. And that new stuff, the hero of our story, is called calcium silicate hydrate, or just CSH for short. The best way to think about it is like a microscopic tangled web of fibers. This CSH glue is the #1 source of concrete strength. The more of this glue you have, and the more tightly packed it is, the stronger your concrete is going to be. But there's a catch. This chemical process, it's not perfectly efficient. As the CSH glue forms and hardens, it always leaves behind these tiny little voids, little pockets of empty space. And this brings us to the real secret behind concrete strength. So let's put our two mixes under a microscope. Because the real difference between our wet mix and our dry mix, you can't see it from the outside. It's all about the invisible structure that forms on the inside.
Just like the researchers from the Indian Institute of Technology Madras put it, the strength is directly linked to its porosity. Porosity, that's just a fancy word for the amount of empty space, those little voids we were just talking about. And the rule is simple. The more empty space you have, the weaker the material is, period.
Okay, now check this out. This is the result of that one little change we made with the water. The wet mix, with all that extra water, ends up with almost 33% of its volume being just empty space. But look at the dry mix. Its porosity is down at 17.7%. That's a huge difference. So here's the bottom line. Just by using less water at the very beginning, our dry mix ends up with nearly 50% less empty space inside it. That means that CSH glue we talked about, it's packed way, way more densely. And to get a little more detailed, it's not just about the total amount of empty space. The dry mix is especially good at reducing the number of the bigger, more damaging voids. You can kind of think of them as leftover water channels, and getting rid of those has a massive impact on the final strength. So less empty space. Big deal, right? So what? Well, let's see how this microscopic difference translates into the thing we actually care about: strength. As in, how much force can this concrete take before it just gets crushed?
And here it is. This is the payoff. Our wet mix, the one full of pores, it can handle about 30 megapascals of pressure. That's pretty good. But the dense, dry mix, it clocks in at a whopping 68 megapascals. The difference is it's staggering.
We're talking more than double the strength, all from just tweaking the water content. You're using the same raw materials to create a fundamentally superior product, all because we optimize that internal structure on a microscopic level.
But, in engineering, there's rarely a free lunch. Gaining all that extra strength, it comes with a completely different set of challenges. It's not quite as simple as saying, oh, drier is always better. So let's look at the final scorecard here. The wet mix has high porosity, low strength, and its main problem is something called drying shrinkage, which happens as all that extra water leaves. The dry mix has low porosity and incredible strength, but its risk is autogenous shrinkage, which is kind of an internal drying that can cause its own set of problems.
So the big takeaway here is this. That small change to the water-cement ratio doesn't just make the concrete a little bit stronger. It literally creates an entirely different material on the inside, with a different internal structure, different properties, and a different set of risks you have to manage.
And this isn't brand new science. Cement itself was patented way back in the 1800s, but this fundamental link between water, porosity, and strength, that was figured out in the early 20th century and really nailed down by researchers like T.C. Powers, whose models are still incredibly accurate today. Which brings us to one last question. If a lower water-cement ratio makes concrete so much stronger, why don't we just use it for everything? Well, that's where the science crashes into the messy real world of construction. You've got to think about cost, how hard it is to actually work with a really stiff, dry mix, and the fact that every single project has its own unique needs. The recipe is key, for sure, but the right recipe always depends on what you're trying to build.